Hey folks, in this section we're going to learn about integrals that yield logarithmic and exponential functions. And so the objectives that we're going to focus on here will be the first one, evaluating a definite integral that's of the form integrate from a to b k over x dx. And then we're going to look at how to integrate using a use substitution. So we've seen use substitution. Hey, remember when we did use substitution, I gave some general guidelines on use sub. I said, I think it was 3 guidelines, but I said something about try letting u equal stuff you see inside parentheses, or try letting u equal stuff you see in the denominator of a fraction, or try letting u equal stuff that you see in an exponent. You're going to see in this section numbers 2 and 3 on my guidelines for u sub playing the game. The third objective is, a familiar topic. We're going to integrate a rate function. And then the fourth objective is evaluating a definite integral of the form integrate a to b e to the x dx. And then we'll look at how use substitution plays a game with exponential function. That's objective 5. And then objective 6, we're going to integrate a rate function. So some familiar topics here. What's going to be really new, though, is the functions, ending up with logarithmic and exponential functions. So I'd like to start off by just reminding us that we know the derivative of ln x is 1 over x. We know that. And we know that if you have a differentiable function of x, then from the chain rule, when you differentiate natural log of f of x, you get 1 over f of x times f prime of x. So we know that. That's old derivative rules. So here we go. Because we know that the derivative of ln x is 1 over x, and we know integration is the inverse operation of differentiation, we get for free that the integral 1 over x dx is the natural log absolute value x plus c. Now I say we get that for free because they're inverse operations. We know derivative of natural log is 1 over x, so the antiderivative of 1 over x should be a natural log. But notice we have absolute values here in our antiderivative formula. And the reason why we have absolute value signs there is it doesn't matter if you differentiate natural log x or the natural log of negative x. You're going to get 1 over x. Think about it. You differentiate natural log negative x. That, according to the chain rule here, our chain rule, if you were to do the derivative of that, you would have 1 over negative x times the derivative of negative x, which is negative 1. So 1 over negative x times negative 1 would be 1 over x. So just remember, when you integrate, smack some absolute values. All right, let's look at our first example here. We're going to evaluate the following definite integrals. In part A, we're going to integrate from 5 to 7, 1 over x dx. And then in part B, we're going to integrate from negative e to negative 1, 10 over x dx. So write down the example, leave yourself some space, and then you're going to see me head off to the chalkboard and work through this example. Hey folks, so we left off with this example. First example, evaluate the following definite integrals. And the first one in part A was the integral from 5 to 7, 1 over x dx. So I put up here in the upper right hand corner of my chalkboard the rule that we just saw, that in general the antiderivative of 1 over x dx is the natural log absolute value x and then plus c. So it looks like for part A all we have to do is get an antiderivative for 1 over x, and that's natural log absolute value of x. And then we're going to evaluate that from 5 to 7 using our fundamental theorem of calculus. So that gives us the natural log absolute value 7 minus the natural log absolute value 5. Or actually, it probably looks better just to say natural log 7 minus the natural log 5. And that's all there is to part A. Part B, we're integrating from negative e to negative 1, 10 over x dx. So again, we get an antiderivative. Antiderivative is 10 natural log absolute value of x. We're going to evaluate that from negative e to negative 1. So the negative 1 goes in first. So we get 10, the natural log of negative 1, minus 10, the natural log absolute value of negative e. And it's important that we have these absolute values here because, well, we know the absolute value of negative 1. Absolute value of negative 1 is 1. So we have 10 times the natural log of 1 minus 10. And then the absolute value of negative e, well, that's e. So 10 times the natural log of e. And we can actually clean this up a little bit more. We know the natural log of 1 is 0. So this is 10 times 0. 10 times 0, well, that's 0. Minus, now the natural log of e, I'm looking right here, the natural log of e. The natural log of e is 1. So it's 10 times 1. So then 0 minus 10 times 1, that's 0 minus 10. 0 minus 10 is negative 10. And that's all there is to this first example, parts A and B. What we're going to do now is we're going to head back to the slides, and because you know it's going to be more exciting than just this. So we're going to head back to the slides, and we're going to look at basically how to use the u substitution when attacking some indefinite integrals. So we're going to head back to the slides, look at an example, then we'll be right back here at the chalkboard to work out the example. All right, hey, I hope it made sense. That example made sense. Moving along, if you're integrating a 1 over u, where u is a differentiable function of x, then the antiderivative of 1 over u du, that should be a du there. 1 over u du is the natural log absolute value u plus c. What do we have here? This is our u sub. This is going to be you know, one of my guidelines that I gave you on u substitution. Let's do an example. You'll see what I mean. Here we're going to evaluate the following indefinite integrals. So part A, it's going to be 2 over 2x plus 5 dx. Part B, it's 3x times the quantity x squared plus 9 to the negative first dx. So you know the drill. Write down the example, leave some space. I'm going to head off to the chalkboard now, and I'm going to work through these examples, parts A and B, and probably have you do a couple of odd number problems after the examples as well. So here we go to the chalkboard. We'll be coming back to the slides here soon. All right, here we are at chalkboard working out the example. The example we saw was evaluate the following indefinite integrals. So this is the first one. Integrate 2 over 2x plus 5 dx. So what we're seeing here is some of our guidelines for u substitution kick in. Remember, in general, our guidelines for u substitution were to let u equal the stuff we see in parentheses, let u equal stuff we see in an exponent, or let u equal stuff we see in the denominator. Here's a denominator. So we're going to let u equal the junk we see in the denominator. So we're going to let u equal 2x plus 5. And then remember, you must always compute du. You must always compute the derivative of whatever you're saying u is. So here du is a 2 dx. Now we substitute in. So we substitute in the denominator, that's u. The 2 dx. 2 dx is du. So we're going to substitute du in for 2 dx. So I'll put a 1 up there. Du, antiderivative of 1 over u. You got it. Natural log absolute value of u plus c. And now we resubstitute 2x plus 5 in for the u. And that's it for part A. So for part B,
Here we're integrating 3x times the quantity x squared plus 9 to the negative first power dx. So again, following our basic guidelines of u substitution, we're going to let u equal the junk we see in the parentheses. So u is x squared plus 9. And then du, remember du, we always compute the derivative of u. That's what du is. So du is a 2x dx. So now when we substitute in, we substitute u for the x squared plus 9. So that gives us a u to the negative first. But notice we still have 3x dx to take care of. My du statement is not 3x dx. It's 2x dx. I need to see a 3x dx there. So remember, this is where we come in and we massage our du statement. And here we massage the du statement by just simply multiplying both sides of the equation of my du statement. Just multiply both sides by 3/2. 3/2 du equals, because 2 times 3/2 is 3. 3x dx. So you see, we're going to substitute 3/2 du. That's what's going to get substituted in for the 3x dx. So we toss in the 3/2 du. We're going to substitute in 3/2 du for 3x dx. And we immediately take the 3/2, since it's a constant, we immediately take that and rip it out front. Okay, now remember, rules of exponents. You have a u to the negative first. Remember, u to the negative first is 1 over u. And now that we see it's a 1 over u, we're coming up with an antiderivative of 1 over u. Antiderivative of 1 over u is the natural log, absolute value of u. And then we resubstitute for our u. So x squared plus 9 is u. So we substitute that back in here for u. And we get 3/2, the natural log, absolute value, x squared plus 9 plus c. Now for this one, part B, I could actually have my answer as 3/2 natural log, parenthesis x squared plus 9, parenthesis. The reason why the absolute value signs aren't necessary here is that for all values of x, x squared plus 9 will be a positive number. It's not wrong if I have the absolute values there. They're just kind of overkill in this situation, but it's not wrong. In part A, I definitely need the absolute values here because there are values of x that would make 2x plus 5 negative. So the absolute values they're necessary in part A. In part B, they're overkill. But you can't be wrong if you have the absolute values. All right, so I need to make sure that you understand this. So you know what I'm going to tell you to do. I'm going to tell you to pause the video and do a homework problem. So what I'd like you to do is I would like you to pause the video, and why don't we try 2 of them. Why don't you pause the video and try number 17 and also try number 21. So go ahead, pause the video, go into the text, try number 17 and number 21, and then once you've done them, restart the video, and I'm going to be right back here at the chalkboard working through number 17 and 21. All right, here, let's see if you got number 17 correct. I would start off here by doing a u sub. I'm going to let u equal the denominator. So u equals 2x plus 3. Then du is a 2 dx. So when I substitute in, my denominator is a u, numerator is a 1, I still have to take care of the dx. Well, if du is 2 dx, 1/2 du is dx. So I substitute 1/2 du in for dx, and I'm going to take that 1/2 and rip it out front because it's a constant, and now it's a pretty friendly problem. Antiderivative of 1 over u is the natural log absolute value of u. Substitute 2x plus 3 back in here for u, and And we get the antiderivative to be 1/2 natural log absolute value 2x plus 3 plus c. So hopefully you got that for number 17. Let's check out number 21. 21, you're asked to integrate x minus 2 over x squared minus a 4x plus 9 dx. Okay, just like in number 17 and just like in the previous two examples, it's a u sub. So following my guidelines, I'll let u equal the denominator. So u is x squared minus 4x plus 9. Du is the derivative. So du is a 2x minus 4 dx. Barely got that dx on the board. I substitute in. So my denominator's u. But I still have to take care of that x minus 2 dx. Notice du does not equal x minus 2 dx. But if I multiply both sides by 1/2 du, that is x minus 2 dx. So I substitute in the 1/2 du for the x minus 2 dx. Take the 1/2, rip it out front. There's a 1 up there. Piece of cake now. Antiderivative of 1 over u is natural log absolute value of u. Substitute that back in here for u. And that should be it. That's it for number 21. So hopefully you got this for number 17. Hopefully you got that for 21. Hopefully you're feeling pretty good about this stuff. Time to head back to the slides because now that we've done some practice with the mechanics of doing these type of integration problems, you know what it's time to do. Head back to the slides and look at an application.
Hey folks, I hope you were able to do number 17 and 21, and that you were able to work through them and get the correct answers, and you're feeling pretty good now about the u sub. Time to look at an application. So let's look at this example. The rate at which the percentage of households in Britain that own a television, I believe in Britain they call them tellies, is changing per year by f of x equals 2.512 over x. X is the number of years since 2000, and f of x is the rate of change in percent per year. And this is valid for x values from 1 to 9. We're going to determine the total increase in percent from 2005 to 2009. So think about it. We have a rate function here. F of x is a rate function. We're asked to find a total increase. Sounds to me like we're going to be integrating a rate function. But let's make sure you have this written down because I'm going to head off to the chalkboard and work through the solution.
All right, the example we just saw, the rate at which the percentage of households in Britain that own a television, that rate is changing per year given by the function f of x equals 2.512 over x. X is the number of years since 2000 and f of x is the rate of change in percent per year. We were asked to determine the total increase in percent from 2005 to 2009. Since x is number of years since 2000, 2005 to 2009 would correspond to x values of 5 and 9 respectively, 5 for 2005, 9 for 2009. To determine the total increase, that means we're going to integrate the rate function. So I immediately set up the definite integral that's going to answer the question of the total increase. We're going to integrate from 5 to 9, 2.512 over x dx. Very straightforward. Antiderivative is 2.512 natural log absolute value of x. We just evaluate that from 5 to 9. And let's see, that gives us a 2.512, the natural log of 9, minus 2.512, the natural log of 5. I crank this through my calculator, and I get something pretty close to 1.47652. So what does this mean? This means, I'll write it down over here. This actually means that from 2005 to 2009, the total increase in households in Britain total households in Britain that own a television, but since we're talking about Britain, I'll say it, they own a telly. I believe in Britain they call televisions telly. Was about, so the total increase was about 1.47652%. Yeah, how about I just say 1.5%. That's all there was to that example. So to make sure we're dialed in, that we understand several things here. One, it's a new function that we're integrating. But secondly, once again, when you integrate a rate function, you're getting a total accumulation, either a total increase or a total decrease. To make sure that we're dialed in on that concept, I'm going to want you to pause the video and do number 73, part B. So go ahead, pause the video, do number 73, part B. Once you've done 73, part B, restart the video, and I'll be back here at the chalkboard and we'll work through it. All right, here in number 73, it says that the housing crisis of the late 2000s not only affected traditional houses, but mobile homes as well. And here's a quote: "With slimmer paychecks, people are wary to take out loans for mobile and manufactured homes, even though they are generally more affordable than stick-built housing." That quote's from James Hargraves, and he's owner of Pennistar Homes. The rate of change in the number of mobile homes manufactured in the southern United States from 2001 to 2011 can be modeled by f of x equals negative 54.1 over x, and that's on the interval 1 to 11. X represents years since 2000, and f of x is the rate of change in the number of mobile homes manufactured, and that's measured in thousands per year. So in part B, you were asked to integrate to determine the total decline in southern mobile home manufacturing from 2005 to 2010. Well, since x represented the number of years since 2000, 2005 is an x value of 5, 2010 is an x value of 10, so we need to integrate the rate function from 5 to 10. We need to integrate from 5 to 10 the rate function. And quite simply, the antiderivative is negative 54.1 ln absolute value of x, evaluated from 5 to 10, so that's negative 54.1, the natural log 10, minus negative 54.1, the natural log of 5. And when you crank this through the calculator, or at least when I crank it through the calculator, I get a number that's pretty close to negative 37.5. Negative 37.5. Well, it's negative. That means it's a total decrease. So, you know what? I'll write down a full-blown interpretation here. How about something along the lines of this? How about the total decline? That sounds good. The total decline in mobile homes made in the southern United States, I'm just going to say in the South, from 2005 to 2010 was about 37,500. So remember your rate function, the function you were given, the rate function, it was thousands per year. So that means this number, I convert it to thousands to get the total decline of about 37,500. So hopefully you got 73 part B, and we're going to head off now. We're going to head back to the slides, and we're going to look at how to integrate exponential functions.
All right, folks. Hopefully that example made sense, and hopefully you're able to get number 73 part B as well. Just more practice with integrating a rate function. Next up is we're gonna attack the exponential functions. So let's remember the following. Let's remember that the derivative of e to the x is e to the x. Remember how we did that in class? Remember it was a fun little exercise. And also remember your chain rule, that when you're differentiating e to some function of x, the derivative is e to that function of x times f prime of x. So e to the function of x times the derivative of the exponent. We will get for free an integration rule for e to the x. So if we know the derivative of e to the x is e to the x, then we know the antiderivative of e to the x is e to the x. So that's why it says the antiderivative of e to the x dx is e to the x plus c. We get it for free. Now let's do a little practice here. This example, we're going to evaluate the following integrals. Part A is the integral 2e to the x plus 4x dx, and part B is a definite integral from 1 to ln 4, the quantity negative 5e to the x plus 7 dx. So you know the drill. Write the example down, leave yourself some space. I'm going to head off to the chalkboard and work through the solution.
All right, hey, we just saw this example. Evaluate the following integrals. Exponential functions. On the surface, they're pretty easy to integrate because we know the derivative of e to the x is e to the x. We know the antiderivative of e to the x is e to the x. Remember, those are inverse operations. So when we look at part A here, and we're asked to integrate 2e to the x plus 4x dx, we just go term by term, and the antiderivative of 2e to the x is 2e to the x. That's pretty friendly. The antiderivative of 4x is 2x squared. Tack on a plus c, and you're done. That's all there is to it. Now part B, well, this is a definite integral, but we attack it the same way. Get an antiderivative. So we get an antiderivative. The antiderivative for the first piece, negative 5e to the x, is just negative 5e to the x. The antiderivative of 7 is just 7x. And we're going to evaluate that from 1 to the natural log 4. So I put natural log 4 in here first. So good grief. Negative 5e to the natural log 4 plus 7 times natural log 4 minus negative 5e to the first plus 7 times 1, which is 7. I'm going to clean this up a little bit. You know we're going to clean this up a little bit more. Check it out. E to the natural log 4. E to the natural log 4 immediately simplifies to 4. So negative 5 times 4 is negative 20. And, well, that's just 7 natural log 4. I can't do much about that. E to the first, well, e to the first is e. So why don't we just distribute this negative 1 to get plus a 5e and then minus a 7. And, geez, I don't know, I guess we could go one more step. You have a negative 20 minus 7. So you could take those two and say negative 20 minus 7 is negative 27 plus 7 natural log 4 plus 5e. I'm not going to go any further. I mean, that's an exact value, and I'm happy with that. So as you know, not all of our integrals that involve the exponential function are going to be just as straightforward as e to the x. So we're going to head back to the slides. We're going to quickly go back to the slides and talk about when use substitution's playing the game. Remember when we first did use substitution, I gave you some general guidelines. Those general guidelines were try letting u equal the stuff you see in parentheses, try letting u equal the stuff you see in an exponent, and try letting u equal the stuff you see in the denominator of a fraction. We saw earlier in this video where the denominator of a fraction was coming into play. That's what we were letting u equal. I bet now we're going to see we're letting u equal the stuff that's in the exponent is going to come into play. But let's head back to the slides, and then I'm sure we'll do an example. I'll be back here at the chalkboard to work through the example, and hopefully it'll make sense.
All right, folks, hopefully that example made sense. Now it's time to handle the u sub part. If u is a differentiable function of x, then the antiderivative of e to the u du, well, that's just e to the u plus c. This is the other guideline I gave you on u sub. You know, sometimes we're going to let u equal the stuff we see in the exponent position. That's what this integration formula is. It's telling us about u sub. So this example, in part A, we're going to integrate 12e to the 4x dx. And in part B, we're going to integrate the quantity 9x plus 7 e to the 9 halves x squared plus 7x dx. So now you know what I'm going to say. Write down the example, and we're going to head off to the chalkboard and work through this example, and then I'm going to have you do a couple of odd exercises. So time to head off to the chalkboard.
All right, here we go, this example. As promised, we have something more exciting happening in the exponent now, not just an x, but there's some other junk happening there. We're going to need a u substitution. So look at part A. I'm going to follow my guidelines. I'm going to let u equal that stuff I see in the exponent. So I let u equal 4x, then du is a 4dx. So when I substitute in, I'm going to substitute in, I have e to the u. E to the u. Notice I still have the 12 dx to take care of. Du does not equal 12 dx. But if I multiply both sides by 3 du is equal to 12 dx. So I'm going to substitute 3 du in for 12 dx. And you're probably guessing I'll put that 3 out front. Now it's pretty friendly. Antiderivative of e to the u is e to the u. Resubstitute 4x down for the u, so we have 3e to the 4x plus c. That's all there is to part A. Part B. Well, look at this mess. We're asked to integrate the quantity 9x plus 7 times e, and look at that exponent of e. 9 halves x squared plus 7x. That looks like a mess, but if we use our friendly u substitution, let u equal what you see in the exponent. The 9 halves x squared plus 7x. Then check it out, du is 9x plus 7 dx. Du is always the derivative of your u statement. So when we substitute in, we substitute u for that nastiness in the exponent, and look, the 9x dx, 9x plus 7 dx, 9x plus 7 dx, that's du. So we didn't have to massage anything at all here. We just substitute du in for the 9x plus 7 dx. And it really don't get much easier than that. The antiderivative of e to the u is e to the u plus c. Resubstitute e to the 9 halves x squared plus 7 plus c. And that's all there is to part B. So there, we've done part A, we've done part B. You know I'm going to want you to do a couple. You know I'm going to want you to practice a couple. So why don't you pause the video, and I have 2 of them for you to try here. number 41 and number 43. So go ahead and pause the video, try numbers 41 and 43. Once you've done them, restart the video and I'll be here at the board cranking through the solution for them. Alright, hey, here in number 41 you were asked to integrate e to the 4x plus 1 dx. Hopefully you looked at that and you just said, well, I'm going to let u equal 4x plus 1. du is a 4 dx. And when you substitute it in, you add e to the u. You still have the dx to take care of. And hopefully you said, well, 1/4 du, that'll take care of the dx. And you substitute a 1/4 du in there for the dx, and you say, ha, I laugh at you. This is friendly now. Antiderivative of e to the u is e to the u. Substitute 4x plus 1 back in for the u. And that's it for number 41. Antiderivative is 1/4 e to the 4x plus 1 plus c. 43, I hope for number 43, you said, you know what? Gonna let u equal that exponent, x squared plus 1. Then du is a 2x dx. Got the dx on the board. Substitute in. Take care of the u. It's e to the u. Then your 2x dx, so nice when du takes care of that. There's no massaging necessary. So substitute du in for the 2x dx. And, whoops, you don't need that. The antiderivative of e to the u is just e to the u plus c. Resubstitute. Put x squared plus 1 in for the u. And that's all there is for number 43. So hopefully you got 41. Hopefully you got 43. Hopefully you're saying, hey, I really like this stuff. I'm ready to go do an application. So let's head off to the slides and let's talk about an application.
All right, folks, hopefully that made sense. Hopefully you're feeling a little more comfortable with u substitution in general, and you're seeing how it's playing the game now, and hopefully you're able to do 41 and 43. I wanted to give you this little integration formula for e to the kx, where k is just a number. It's a non-zero real number. If you're ever asked to integrate e to the kx dx, you could go through u substitution. You could let u equal that kx and then determine du and do a u sub. But that u sub gives us this little formula that the antiderivative of e to the kx dx is 1 over k e to the kx plus c. I'd know this formula if I were you. This is a little formula that I found to be very handy, very beneficial through my math career. Just the number of times integrating something of the form e to the kx dx has popped up. Well, it's popped up quite a few times, and it's always nice to know quickly what the antiderivative is. So I would, what is that? No, I'm not going to do that. Sorry about that. That was very rude of my computer to do that. So I would know this formula, and let's see how we can apply it. Notice I'm just going to mention one more time. This formula is just special. It's a special case of u sub. Let's see how I'm going to apply it in this example. In this example, we're given that the rate of change in the amount of recovered paper in Brazil can be modeled by f of x equals 130.115 e to the 0.053x. X is the number of years since 2000, and f of x is the rate of change in the amount of recovered paper, and that's in thousands of metric tons per year. And this is valid on the interval 1 to 11. So here we're asked to evaluate and interpret the integral from 6 to 11 f of x dx. So before I head off to the chalkboard, f of x is a rate of change function. I'm going to integrate a rate of change function. So even before I do anything, I know that when I integrate a rate of change function, I'm going to be determining a total accumulation. It's going to be a total increase or a total decrease. But in any event, go ahead and make sure you have the example written down. I'm going to head off to the chalkboard and I'm going to work through this example, and then I'm going to have you do one problem to make sure that you're completely dialed in. So see you at the chalkboard.
Hey, before we talk about this application, when we look at this application, I wrote something up here on the board that was on the slide, and I want to go over it one more time. We can use U substitution to show this little formula up here is true. But it's a really important, handy formula for you to know. In other words, whenever you're asked to integrate e to the kx dx, it has to be of the form e to the kx. K is some number. And just one single term up there, and it's linear, e to the kx. Just knowing, without doing any work at all, just knowing that the antiderivative of e to the kx dx is 1 over k e to the kx plus c, that can save you a lot of time. It's also going to come in real handy when we get into chapter 7. So I would kind of know that quick little formula. Hey, let's take a look at this example. The example said the rate of change in the amount of recovered paper in Brazil, so that's like recycling paper, can be modeled by f of x equals 130.115 e to the 0.053x. X is the number of years since 2000, and f of x is the rate of change in the amount of recovered paper in thousands of metric tons per year. So x is the number of years since 2000. F of x is a rate function. The example said, let's evaluate and interpret the integral from 6 to 11 f of x. I'm going to go ahead and I'm going to write f of x in here. So we're going to evaluate and interpret. So we're evaluating and interpreting. See, this is a rate function. I bet my interpretation is going to have something in there about a total increase or a total decrease. But let's go ahead and evaluate first. Notice, doing this antiderivative, that's where that little formula comes in. It's really handy. We don't have to do the u sub. It's the u sub that gives us that formula. So we can immediately get the antiderivative here. The antiderivative is 130.115 over 0.053 e to the 0.053x. And we just need to evaluate that from 6 to 11. And when I crank this through the calculator, I'm not going to show the calculations because I'm cranking it through the calculator, I get a number pretty close to 1023.8. So we've evaluated. Now let's do the interpretation. Remember, x represented the number of years since 2000. So that's 2006, that's 2011. So from 2006 to 2011, the total increase, positive number, it's a total increase. The total increase in recovered paper in Brazil was about 1,023.8. Now that was in thousands, so it's 1,000, and it was metric tons. So from 2006 to 2011, the total increase in recovered paper in Brazil was about 1,023.8 thousand metric tons. I don't know if you want to say 1.0238, million metric tons. I like that, 1,000 metric tons. So you know what, I'd like you to practice one. I'd like you to practice one because we're using this handy dandy little short formula to kind of expedite our work here. So I'm going to want you to pause the video and go try number 75, part B. So give that a try. Once you've done it, restart the video. I'll be here working through the solution. Alright folks, here in 75 part B, it said that fueled by rising unemployment and food prices, the number of Americans on food stamps has been steadily increasing. The number of participants in the federal food stamp program from 2000 to 2010 can be modeled by f of x equals 1.06 e to the 0.06x. X represents the number of years since 2000, and f of x represents the rate of change in the number of participants in the food stamp program, and that was measured in millions per year. In part B, you're asked to evaluate the integral from 0 to 8 f of x dx and interpret. So you're asked to evaluate from 0 to 8 f of x dx and interpret. You're asked to evaluate and interpret, well, we're integrating a rate function. You integrate a rate function, I think that total increase or total decrease is going to be in the interpretation. But let's go ahead and get the antiderivative. Notice I left that little handy dandy formula up there. It's going to make my work here go really quick. I can quickly get the antiderivative to be 1.06 divided by 0.06 e to the 0.06x. And then I use my calculator, crank this through the calculator, and I get 10.88. Time for the interpretation. I'll write the interpretation here. So x represented the number of years since 2000. So 0 would correspond with 2000. 8 would correspond with 2008. So from 2000 to 2008, the total increase. Not a surprise to see that, huh? The total increase in the number of participants in the food stamp program that total increase was pretty close, so I'll say was about 10.88, so 10.88 million, and I guess I'll just tack on people. So hopefully you got 75 part B. Hopefully you're seeing the advantages of that handy dandy little formula. Hopefully this is making sense. Hopefully you did everything that I asked you to through this video. You feel really confident about now attacking the homework problems in section 6.5. So go ahead and attack the homework in 6.5. Good luck on getting through the homework. I think you'll do a fine job. And thanks for watching.